Hello, the following presentation is based on the original test paper in trigonometry from the year 2018 and demonstrates solving the third most advanced question in this paper. I will read the question. You know the following: a equals 7, tangent alpha equals 1, tangent beta equals 4/3. Find the length of the other two sides of the triangle. Note that this is not a right triangle. First thing, I will name the other two sides as B and C. This triangle is not a right triangle, but I can create right triangles by dividing this triangle like this, with two right angles here, and I will also name the division line H for height. The basis edge A is now subdivided into two segments, which I will call X and Y, and also write a equation A equals X plus Y. Now, with completed preliminaries, we can start writing trigonometrical equations. So, tangent alpha, it's opposite over adjacent, so H over X. Tangent beta is H over Y. From the first equation, by multiplying both sides by x, I can derive that H equals X tangent alpha. And from the second equation, we get H equals Y tangent beta. Now, the left side of both equations is equal to H, so the right sides must also be equal. Therefore, I can write that X tangent alpha equals Y tangent beta. At this stage I will substitute the concrete values, so tangent alpha equals 1, therefore it's x times 1, x equals Y tangent beta is 4/3 of Y. I will now substitute this expression for x to our previous equation A equals X plus Y. A equals 7, therefore I get 7 equals x is 4/3 of Y, 4/3 of Y plus Y. And this now is equal to 4/3 of Y plus Y can be presented as 3 over 3Y, that's the same thing as Y, so 4 plus 3 is 7/3 Y. Now, multiplying both sides by 3, I get 7 times 3 equals 7y. And dividing both sides by 7, I get y equals 3. So that's the first meaningful result. From the equation A equals X plus Y, I quickly get X must be equal 7, A is 7, minus 3, it's for Y, X must be 4, because 3 plus 4 is equal to 7, or A. Now I can use this previously written equation to find the value for H. H equals X, now I know it's 4, times tangent alpha is 1, so H is equal 4. I should be also able to get the same result from the second equation, so Y is 3 times tangent beta is 4/3, 3 times 4/3, it's 4 as well, so everything is alright. Now I have most edges in both triangles known, so I know H, I know X, I can find B from the Pythagoras theorem. B squared equals H squared plus X squared, h squared is 4 squared, and x squared is also 4 squared. So it gives me 16 plus 16 versus 32, so b will be square root of 32. But square root of 32 can be presented as square root of 2 times 16. Now, square root of 16 is 4, so I get 4 square roots of 2. And that's the first result for the side B. Now, side C, also from Pythagoras, c squared equals h squared plus y squared. H squared is 4 squared, and y squared is 3 squared. So I get 16 plus 9, this is equal to 25. And c is square root of 25, square root of 25 is 5. So the task is solved.
In this solution, I used concrete values that were substituted into formulas relatively early. Technically, there is nothing wrong with such approach, but if you solve problems for programming, you are unlikely to know your actual values before the runtime. So quite often we have to provide a solution in a fully symbolic or algebraic form. You might say we need to think like a programmer. So all this stuff is in the symbolic form anyway, up to this point. And now I will take a new sheet of paper. Here it is, to have some space for the fully algebraic solution. So from the equation we had, I will find x by dividing both sides by tangent alpha. So x equals y tangent beta over tangent alpha. And now the process of substituting the expression for x into our equation a equals x plus y. But without concrete values, it is a equals x. We have expression for x here, so just copying it in. Tangent beta over tangent alpha plus y. And we have an equation which we can solve against y. So first of all, I will extract y, having in the bracket tangent beta over tangent alpha plus 1. Let's process this addition. 1 can be represented as tangent alpha over tangent alpha to get a common denominator. Therefore, a equals y, a fractional line, tangent beta or tangent alpha plus tangent beta in this sequence over tangent alpha. And from this we can now find the final value for y. Therefore y equals a times tangent alpha over tangent alpha plus tangent beta. And that's the expression for y. The next step, as we did previously, will be to find the h. We can't use this formula because we only have y at the moment, so it has to be this formula. So h equals, we have the expression for y, so it's a tangent alpha over tangent alpha plus tangent beta. Okay, so this was this expression multiplied by tangent beta, and that's the expression for h. H will be one of our final result formulas, so I will draw a frame around it, And now we're ready to use the Pythagoras theorem, because we already know h and we know y, so we can easily find c. So c squared equals h squared plus y squared, and c is square root of h squared plus y squared. This is another final result, so it goes into a frame, as well as the y value, which we also have used in this equation. One more final step now is to apply the Pythagoras again to find the b as square root of h squared plus x squared this time. This formula goes to a frame as well, and the very final thing, x equals a minus 7. Oops, a minus y, of course. One more look at the assorted results. 5 different formulas? Shouldn't be there only 2, one for the b edge and one for the c edge? As long as we remember the goal of this exercise, the firm answer is no, or at least not necessarily. If the goal is to think like a programmer, then, well, we have here everything that we really need. Actually, the h formula is already over-calculated. In programming, we should keep things simple, so why not this version of this formula? It will actually make calculations a bit faster because we avoid multiple tangent calculations. Everything can now be easily calculated from the predefined input data. This is the corresponding code in C++. Run the program and get the results. 5 and 5.65685, which stands for 4 square roots of 2. And just in case, if you'd really love to have a single formula for B and a single formula for C, it's not overly complicated. Here they are, complete with the C++ code, but what looks better mathematically in coding is not necessarily better. This code is in fact less efficient, as it calculates the tangent 8 times contrasted to 4 times in the previous version, and possibly even 2 times in the most optimal version of the C++ code. This most optimal version is not shown here, but you can do it on your own. Thank you for watching.